am delighted to be back here in Putney after having spent a lot of 2006 and the beginning of 2007 coming up here frequently and interacting with our volunteer group and doing a lot of research all over this landscape to try to understand Putney and its history and how it came to be the way it is today. And it's really fun to revisit this in my mind. This has been one of my favorite landscapes. Really, I don't have to tell any of you how beautiful it is here. So it's really fun to get to go back and think about these stories again. And I wanted to ask if how many of you made it to at least one of those original presentations? Okay, so we have a bunch of new people. That's great. So I'll say a little bit more about the project, just for those who weren't at those presentations and maybe didn't hear much about what it was that we were doing exactly. The project was sponsored by the local Conservation Commission along with something called the PLACE program, which is a partnership between the University of Vermont and Shelburne Farms. And they've been working together for about 10 years to partner with communities all through Vermont and really in depth consider the past, the history of those communities from all these different angles, from the natural landscape to the cultural landscape, in an effort to both understand the present community and also have more tools for looking to the future in a more rich and with a rich and relevant context. So that's where the framework for this project comes through the work of the PLACE program. And then the Vermont Land Trust was another sponsor. And as always, I'm standing up here by myself, but what I'm going to present to you tonight draws on the knowledge and work of a lot of different people. So I want to just give a few thanks and acknowledgments before I dive in. First off, I want to thank Ann Carey, who I know some of you know. Ann was on our core team of local volunteers who helped do research on the landscape and do logistical organization for this whole project. And Ann was in the research department, sort of our gold star core team member. She just intrepidly dove into these very difficult scientific topics with no background at all. She was just fearless and totally amazing. And she got really interested in thinking about the local hydrology and especially thinking about how water moves through the landscape, moves through bedrock, which is an extremely difficult thing to investigate. And she found some ways to look at that, and I'm going to present some of what Ann found. Additionally, John Warren, who's also here tonight. John was my local geology guide. He's a geologist who lives in Dummerston. And he spent a lot of time with me just helping me learn the local geology and get the story right and leading field walks and all sorts of things. And he continues to be a great resource for the area and leading field walks and so forth. And Chris Nitch, who's not here tonight, was at the time a UVM graduate student who worked on this project as his master's project. And just he helped out with research and was just, as the people who interacted with him know, just a delightful person to have around in all respects. Then we had a whole slew of regional experts, from around Vermont and some in Massachusetts that we consulted with on particular questions and got guidance from. And additionally, Ann got some help from a bunch of different local people and local Vermont resources for her hydrology research. So I wanted to give a tip of the hat to all of those folks. And then finally, last but certainly not least, the rest of our core team group of volunteers who helped in many different ways to make this possible. So, without further ado, landscapes are really intricate and complicated things, entities. And I think, it's a habit of a lot of us to sort of think of them as kind of static. We think of them the way they are now. If you've lived in a place long enough, you think of the changes that you've seen in your lifetime, which sometimes can be fairly remarkable. A lot of us move around a lot these days and don't really get the opportunity to see a landscape undergo changes in our lifetime. If we take the long view, landscapes change just mind-bogglingly over long periods of time. They're not static at all, and even as I speak, there are things changing and flowing and rearranging on the landscape around us. So that's a big part of why we take this view of looking into the past to try to better understand the present. And actually, John Warren supplied me with this quote that I just love, that sort of speaks to this idea about landscapes. Landscape is an event rather than a thing. The landscape is more than just a source of visual inspiration, although it's that too. It's a storied place, a dwelling place dense with memories of lived relationships and quickened emotions. Its visual power derives as much from its evocation of human presence and embodied histories as from its unique geology. I would add a couple of main points to that really focus in on the topic of tonight's talk, which is the geology. And one thing, the author of this quote is talking about the human history that's embodied in the landscape. And that is something that I think really touches people's hearts probably the most. But it turns out that the rocks are also contain embodied histories. And one thing that I want to do tonight is look into those histories and try to read and interpret some of those stories. And they are the deepest, most ancient stories of any place are contained within the rocks themselves. They tell of how this landscape was actually formed, how the very land that we're on was formed. So those are stories that most people miss. You know, sometimes we're keyed into some of the human stories that we can see signs of on the landscape that touch our hearts. But most of us don't know anything about how to look at the hills and the rocks and the sand and the water and see a story in that. So that's what tonight is going to be about, trying to sort of wake up that part of the landscape and story that element of the landscape. But the other piece that I would also add to her quote is that all of the human stories on the landscape and the stories of the plants and the animals that live here are all being acted out on the stage that's set by the geology, by the land itself. And so geology, which a lot of people don't think about much at all, really is influencing so many things about how this landscape has evolved over time, how people's lives have played out here, how plant and animal communities are arrayed on the landscape, and so forth. So that's another thing that I hope to kind of bring to the forefront in this talk. And there's two main elements of the geology that I'll cover in sequence. The first is the bedrock geology. So the story of the solid rock that's part of the Earth's crust that is under absolutely everything. And then, in addition to that, there are what are called superficial deposits, which are smaller bits of mineral material, sand and clay and gravel and boulders and so forth, loose bits of rock that sit on top of the bedrock, and that has another layer of history and significance. So we'll talk both about the bedrock and then these superficial deposits. And in addition, we'll get a little bit into the local hydrology through some very particular investigations that were initiated by Anne. And this all, sets the stage for what we talked about in the full series of lectures, the series of 3 lectures. The next lecture, which you'll be able to get on DVD, was focusing on the human landscape, the cultural landscape, how people have been shaped by and shaped the landscape of Putney. And then the final lecture is on the plant and animal communities, and all of these different topics are sort of interrelated. So I'm going to start out by telling just one particular story on Putney's landscape that connects in a really surprising way to the geologic history here. Mostly it's just an example of how unexpected some of these connections can be between the local geology and other things that are happening here. This is the top of Putney Mountain, and every fall, a small group of intrepid folks, some from local, some from farther away, gather on the top of Putney Mountain to observe and count hawks in their annual southward migration. And it turns out that Putney Mountain is an excellent place for watching hawks, and it's one of the premier hawk watching and hawk observing places in the whole Northeast during the migration. And in that time of year, which is already past at this point, many different raptor species are seen flying over the top of Putney Mountain. Turkey vultures, as an example, red-tailed hawks, broad-winged hawks, all manner of different raptors. And it's no accident that Putney Mountain is a good place to watch this phenomenon. As it turns out, raptors tend to be more gliders in their flight than they are flappers, which means they need a lot of help from air currents in order to make their migration and have enough energy to do that. So they're really savvy to how air currents develop and move across the landscape. And the air currents are, this is just to note that I think this is from the fall of 2007. The volunteers up there counted 3,430 raptors as they passed over the top of Putney Mountain. The shape of the landscape itself has a big influence on air currents and how they develop and how the hawks might be able to use them to help out in their migration. This is an aerial view looking north. This is Putney Mountain here, and looking north up this ridge line all the way. This is Mount Ascutney in the background. And you can see that there's a ridge line that sort of noodles its way up almost all the way to Mount Ascutney. This is a view of the same thing, only in Google Earth, with Putney Mountain right here, I believe, and then you can see this ridge line going up, and again, Mount Ascutney in the background. And you can see that it just really stands out as a very prominent, very noticeable topographic feature on the landscape regionally. And it turns out that this feature has a big influence on how air currents develop in this area. And biologists think that a lot of raptors are already following the Connecticut River Valley as sort of a road that is going to take them south. So they're already sort of concentrated in the Connecticut River Valley. But then in the fall, a lot of winds are coming out of the northwest. And as they come down, they strike the side of this knife ridge line, and they get deflected. They get deflected upwards, and they also get deflected to the south. And this provides just what the birds are looking for. They get both a lift up high into the air where they can soar and get a lot of height and just continue to soar, and they're also getting shuttled southward at the same time. So the ridgeline just provides this great environment of air currents, and the birds have learned that, and they've come over time to come to this place so that they can get an extra push on their southward journey. Oh, one more arrow. If we drape the Bedrock Map of Putney over this same landscape, this is mapping out the different types of bedrock that geologists have identified in the town. There's a transition from one bedrock type to another that runs right along the edge of this ridgeline. And so there's a hint that there's something about the actual rocks underlying that ridgeline that's creating that landform, and that's creating this ridgeline that the birds are using in their migration. So what I'm going to do is go through the history of the rocks and try to understand what is forming that ridgeline. How did it come to form in the first place? in this fantastic way that sort of interacts with the biological life of the area. And before we get too deeply into that history, I want to just first do a general orientation to the rocks of Putney. And what are the rocks that are mapped out here? What are the different bedrock types, and where do you find them? Well, the map looks fairly complicated. It looks like there's a lot of things going on geologically here. And in some ways, there are. But we can take comfort in the fact that despite all the variation it looks like there is on the map, there's one main rock type that accounts for a whole, really most of Putney's landscape. And it's found in some measure in all of these different mapped out units. And that rock type is schist. And schist is a rock that starts as muddy sediment, fine sediment like silt and clay, usually collecting in the bottom of a large body of water. And that mud turns to rock over time. And the first kind of rock it turns into is called shale. And if that shale gets squeezed and heated and crunched just right, it can become schist, which is what we have in great abundance here in Putney. Here are some different pictures of schist. It can look pretty different in different locations, but schist, one sort of unifying feature is that it's layery, and oftentimes those layers are sort of ripply. And if you see them in just the right light, if you see a surface, they're shiny. They have what a geologist would call schistosity. And post-geologist. But the shininess is created by mica crystals, and the mica crystals are flat, and they also are creating the flaky, layery quality of the rock. And the mica is something that develops during this process of metamorphosis, where the shale is being squeezed and pressed, and the mica crystals form during that process. So this is the major rock type in Putney. And also the stone walls that snake through the woods in a lot of different parts of town also really bear out the dominance of schist on this landscape. So many of the rock walls are just almost 100% chunks of schist. And incidentally, they also, when you see them in the rock walls, you'll notice that they often have this kind of flattened shapes. You know, they're, I don't know how to describe them, but they make sort of nice things to pile on each other, because instead of being rounded and irregular, they're often flat, and that's again because of that mica layering. In a couple different bands through the town, the schists are mixed in with another rock type that's very closely related. It's called slate, which most people have heard of slate. And slate starts out just the same way as schist, as muddy, fine sediments in the bottom of a body of water. And the only difference is it doesn't get heated and squeezed as much as schist does. So if you took slate and you kept squeezing it and putting pressure and heat just the right way, you would then get schist. And it also has that same layery, sort of flat layered quality that schist does, but instead of having the wavy, rippled, distorted layers, the layers are really flat. And that's what allows you to use it for so many things like roof slates and billiard tables and all the things that people have used slate for through time. And there is actually an old slate quarry in Putney. I have a picture of it. Yeah, this is a picture looking at, you know, the sort of the shape of where they've extracted the rock. It was probably a 19th century slate quarry. And there's a star that's popped up here that shows the location. I think that's along Signal Pine Road, if I'm remembering correctly. So we can see that people in the past were actually using the local slate, probably for roofing and that sort of thing. There's another really neat and important rock type in town. It's found mostly in this swath in the western part of town. But there's this formation just to the east also contains it in somewhat lesser quantities. And this rock type is marble. Marble is mostly composed of calcium carbonate, and it starts out as the detritus of marine organisms. They're shells and exoskeletons that are made of calcium carbonate, and as the organisms die, their bodies float down to the bottom and can accumulate. And those shells and so forth can get cemented together over time, and they become limestone. Now, if those get squished and subjected to pressure and heat, it becomes marble. So that's what's happened on this landscape. And this is a chunk of the local marble. You can see it's not that prepossessing and doesn't really call to mind what most people think of when they think of marble. And that's because the local marble here is fairly impure. And the impurity in the local marble here started out as sand that was getting mixed in with those shells and so forth that we're collecting on an ocean bottom kind of setting. And oftentimes this is a chunk that's had a good bit of time on the surface, and it's been weathered by the elements quite a bit. And this rock typically gets very spongy and kind of pockmarked. It's very recognizable. It's not common to come across a chunk of it on the surface of the land, but if you find one, you'll know that you're looking at this local impure marbleite. What's happening is that the part of the rock that came from sand is very resistant to weathering, and the part of the rock that is made of calcium carbonate is soluble in water. And so the calcium carbonate parts of the rock are getting washed away and leaving little pockets, little holes in the rock in between what were the sand grains. So you get this spongy, kind of pockmarked, funny-looking rock. And that is the Putney marble. And marble is, whenever you see it on the landscape, you see that it has a noticeable effect on a number of different important qualities of the landscape. And one of the things that it tends to influence are the plant communities that you find growing in any given place. And that's because of the calcium carbonate that's in the rocks. That calcium carbonate tends to lend calcium and carbonate to the soils that are found in association with that bedrock. Calcium is an important plant nutrient, so you get soils that have elevated calcium, and there are certain plants that really like that and depend on that. The carbonate also buffers soil acidity, so you tend to get sweet soils in places where you have marble bedrock. They tend to have more nutrients than the typical acidic New England soil. So you get a special suite of plants and plant communities that really thrive on this elevated nutrient setting, this elevated calcium and so forth. And you really won't find them in other places on the landscape. And one of my favorites is the hepatica, which is a very subtle little plant, but it's one of the very first things to bloom around here in the spring. Just a beautiful, sweet little flower, a couple inches high. And another spring bloomer, the bloodroot, is also associated with these nutrient-rich sites. Another important way that marble influences the local landscape has to do with how water moves through the landscape and where you can find it. Because the calcium carbonate is soluble in water, in marble bedrock, it's common to get big channels getting washed out where water is trickling through the rocks, and it just washes it away, creating caverns and solution channels and so forth, places where water can really readily just rush right through those rocks in a way that it's not able to do in the schist and slate type rocks. The local marble, because of the impurity, probably doesn't wash out in these big cavern styles, but it can get spongy and porous and create passages for water to move through. And surprisingly enough, this actually has a direct influence on our lives. Most people in Putney, if you're not right at the village center, are getting your water from a bedrock drilled well. So it's water that's been trickling through little cracks in the bedrock. And this is data that Anne got as one of her projects. This comes from the Cushing and Sons well drillers records. And we took all their records and we mapped them in the community and looked at what type of bedrock those wells were drilled in. And it turns out there's a big difference between wells. The green squares represent wells that were drilled in rocks that had this marble content. And the red squares are wells from rocks that were wells that were drilled into the slate and schist rocks without a marble component. And the two main things that jump out here are, this is the flow rate of the well along the x-axis, and then the depth that they had to drill to get sufficient flow. And you can see that these marble wells really are the high-producing wells. The only wells that were getting up to 20 gallons a minute in bedrock were drilled in these marble-based rocks where there's just bigger channels for water to move through. Also, they didn't have to dig nearly as deeply in the marble-based rocks to get sufficient flow, whereas in some of the schist stuff, wells as deep as 800 feet deep, they had to drill to get any water at all. So it looks like there's good evidence that there's really a lot more water moving through the marble-based rocks in town, and it influences how readily we can get water, to lead our everyday lives. And there's one more set of rock types. Found in a couple small places, these little bands through the center of town and also in this area in the eastern part of town. And these are both rocks that formed from different types of volcanic deposits. These don't outcrop many places in town, but you can see this rock, which is a sort of a volcanic schist along Old Route 5, the conservation area that's right along there. I'm forgetting the name. Aiken, yes, thank you. The Aiken Preserve there, the ledges that are exposed along there have some bands of this. It's got a characteristic sort of greenish hint that stands out from the surrounding schists. And it seems like those formed when the muddy sediments that formed the schist got mixed in with volcanic sediments, most likely something like volcanic ash. And it just formed a schist that had this volcanic component to it. And the final rock type is something called Amphibolite, which this is a picture of a typical schist rock wall with just one stone of Amphibolite mixed in. And it really stands out from the schist. It's not layered, and it tends to be very dark with either light spots or stripes to it. And Amphibolite starts out actually as lava that cools and forms basalt. And like all the other rocks in town, at some point it got crushed and heated and altered from basalt to Amphibolite. So we have two main origin points for all the rocks in town. They all either started out in some kind of marine setting, a deep water setting, or they started out as some kind of volcanic material. So we have the schist, slate, and marble, all things that started out as sediments of some kind in a deep water environment. And then the Amphibolite and the volcanic schist indicating volcanic activity in the area. So right there we can see that in the distant past, this landscape was just so unbelievably different. We're talking about a deep water marine setting and volcanism, which is very different from the sort of quiet rolling farmland and so forth of Putney today. This is my computer deciding that it's time for a break. Oh, look, isn't that pleasant? Putney? All right, I think we're back on track. I don't know why we have this white border all of a sudden, but. So, in any case, this landscape over the period of millions of years has been through changes that as profound as you can possibly imagine. And rather than just continue to tantalize you with all this, I'm actually going to dig into what those changes were and how geologists have put together the evidence they find in the rocks and try to reconstruct what actually happened here over millions of years to create the landscape and the rocks that we have today. That's the what happened here question mark. So in order to understand any of this history, we have to refresh in our minds the idea of the theory of continental drift. The idea that the continents are actually moving around the surface of the Earth. They're not just these fixed things that always stay the same. So if we go back in time from the modern world's arrangement of continents, this is how geologists have reconstructed the placement of the continents over time. So now we're 100 million years ago, almost 200 million years ago. And a lot of people have heard of the theory of the supercontinent of Pangaea, a time when today's continents were actually united in this one massive continent. So this, around 200 million years ago, this is around the time of Pangaea when the evidence shows that the continents were actually together. Well, it turns out in order to understand Putney's rocks, we actually have to go back even further in history, back before the time of Pangaea, before the continents had actually ever come together to form Pangaea in the first place. So this at 200 million years ago is not long enough ago for us to understand the events that actually shaped the rocks here in Putney, which are a good deal older than this. So if we go back even farther, this is about 500 million years ago. This is how geologists have reconstructed how the continents might have looked back then, which boggles the mind that they could even imagine what it might have been. But this is what they've pieced together from the evidence that we have in the rocks today. So it's dramatically different, obviously. North America, or what is to become North America, I'm going to call it Proto-North America, is down at the equator, turned on its side, and most of the landmass is actually underwater at this point, with just this brown area kind of sticking up. And the star is Putney. So Putney does not exist yet at this point, 500 million years ago. It's somewhere off the shore of Proto-North America, underwater in a tropical ocean. So to sort of help connect this strange altered geography to what we have today, this is sort of a cross-section of the coast of Proto-North America, right around the latitude or longitude where Vermont would be forming. And the landmass that's actually sticking up on the shoreline there is where the Adirondack Mountains would later form. And actually, the rocks of the Adirondacks had already been formed at this point. They're about 1 billion years old. So they hadn't been pushed up at this point into the Adirondacks, but the rock itself had been formed. And on the continental shelf, the shallow water environment is where the future rocks of the Champlain Valley are going to form. And then out in the deeper water, deep ocean basin setting is where the future rocks of the Green Mountains are just beginning to form at this point. And these rocks are starting to form as different kinds of sediments being deposited in different kind of settings in this marine sort of transect here. So if you can imagine sediments just steadily accumulating over time, layers upon layers, hundreds and thousands of feet of sediment building up over millions of years. And the sediments are different depending on where you are, as most people are familiar with the sand and so forth that you tend to find on a beach. So the shoreline settings are getting these sandy deposits, sands and gravels. A little deeper on the continental shelf, you're getting coral reefs forming and so forth that are later going to become the limestones that you find on the islands in Lake Champlain and so forth. And then out in this deep water setting, we have these fine muds, silts, and clays, which are just the kind of sediments that formed the rocks here in Putney and also the Green Mountains. So we've created one of the main, sort of recreated one of the main environments that we required to get the rock types we have now, and that is a deep ocean setting with these fine sediments collecting at the bottom. But another commonality of all our rocks is that they've been altered. They're metamorphic rocks, so they started as sediments, but they've been subjected to intense forces of deformation to become the rocks they are now. So we need something else to happen here to create the right environment to get the rocks that we have today. And that something was hovering off the shore of Proto-North America. Here, the continent of Baltica at some point actually started, Baltica and Proto-North America started to converge and actually come together on a collision course for one another. So this tropical ocean where the rocks of Vermont are forming is starting to close at this point. And as that happened, the ocean floor actually had to break under this pressure of the continents coming together. And it broke, one piece was pushed down beneath the other and slid down into the Earth's mantle, into the hot Earth's mantle. And the crust began to melt in the Earth's mantle. And that melted crust started to rise up as magma and form a chain of volcanic islands that were now hovering offshore Proto-North America and getting steadily pushed closer and closer to the shoreline. And periodically erupting and mixing volcanic materials in with the muddy sediments that were already gathering on the ocean floor. So this volcanic island arc is sort of making a beeline for the coast of Proto-North America. And as it does so, it starts pushing up all of these sediments, just plowing them up, and exerting a tremendous amount of force on them, bending them, warping them, and pushing them up into a massive range of mountains that would later become the Green Mountains that we have today. And just a little geography here. These again become the rocks of the Champlain Valley, and the ocean bottom sediments become the ancestral Green Mountains. And this volcanic island arc, future Putney, excuse me, I don't mean to leave Putney out. The rocks of Putney have not yet formed at this point. We're still waiting. And parts of New Hampshire, actually, this volcanic island arc became parts of New Hampshire. So you can still find remnants of these old volcanoes to our east. And the ancestral Green Mountains would have been massive mountains, maybe on the order of the Colorado Rockies, or even maybe getting towards the Himalayas in scale, 15,000 feet high maybe, or 20,000 feet high potentially. And in that time period, since about 400 million years ago when those mountains were pushed up, all that's happened is just millions of years of erosion. So they started out as these massive mountains, and they've just been whittled away over hundreds of millions of years to be the 3,000 foot or so mountains of the Green Mountains that we know today.
Does that continue to happen?
Yep,
Okay.
absolutely, yeah. So we still haven't dealt with Putney, but the rocks of Putney actually formed in a very similar way to the rocks of the Green Mountains to the west. After this collision, there was a basin here that was still filled with water, and those ancestral Green Mountains started to erode, and the little bits of rock and sediment were piling up in this little basin, just as they had been piling up on the floor of that earlier sea. And over time, also shells and so forth were getting mixed into some of the layers, and that gives us the impure marbles that we have in town today. And periodically there was still some volcanic eruptions happening and mixing volcanic activity in with the silts and clays that were collecting in that basin. And again, we need another sort of cataclysmic event to provide the force needed to create the metamorphic rocks that we have in Putney today. And basically we have on deck yet another continent getting ready to crash into Proto-North America. It doesn't really look probable in this diagram, but this little slip here that was called Abylonia, geologists have named it Abylonia. You can see better in this diagram. This is Abylonia here getting ready to dock onto Proto-North America. So we have yet another collision on the horizon. And as this additional continental mass sort of docks and attaches itself to Proto-North America, it's exerting similar intense pressures on all the rocks that have been deposited here. If we kind of zoom in, take this area and expand it up here to look a little bit more at what was happening in a very simplified way, all of those layers of sediments that had lithified or turned into rock got warped and bent and twisted during this second continental collision. Well, there was one more thing I wanted to say. So this collision, in addition to folding the rocks, also created the metamorphic rocks that we have, the schist and slate and marble and amphibolite that started out more as sedimentary rocks. There's one more sort of element of the local rocks that I want to try to understand here before we move on, and that is not just what the rock types are, but the pattern of how they're laid out on the landscape. There's this really distinctive north-south bands of different kinds of rocks sort of progressing across the landscape. If we go back to our folded layers, and we imagine eroding those layers over time, just rock getting slowly weathered away over millions of years. And we look at what patterns of layers you would see on the surface after that erosion. You'd see a pattern of stripes or bands across the landscape, perpendicular to the direction of the force that created the folding in the first place. And if we go back and look at the Bedrock Map, that's exactly what we see here in Putney. So we're basically looking at, well, I've got another picture that shows it a little better too. Again, we can see the force was coming from this direction, the west and the east, squeezing this way and folding the rocks and creating these north-south trending layers of rock. We kind of turn it to the side and look at project what those rock types at the surface might look like going down. You can see again that we're looking at these different layers that actually started out horizontally as sedimentary layers and got tilted and folded during this collision event, and then eroded down to show the striping, banded sort of pattern of rocks that we see today. And also, incidentally, during the process of erosion, acting on the different types of rock is what has created that distinctive Putney mountain ridgeline. Basically, as things erode, different rock types erode more quickly or less quickly than others. Just like I was talking about the marble being, the calcium carbonate being water soluble. So calcium carbonate rocks tend to weather a lot more quickly because the water is just dissolving them and carrying them away. And other types of rock on the landscape are really resistant and hard and don't weather quickly. So the things that don't weather quickly start to stick up and become hills and mountains and ridge lines. And this is that ridge line right here, and a band of very resistant type of schist is underlying that ridge line and creating that north-south straight ridge line feature. And there's one more sort of product of these differing weather abilities of the local rocks that I think is really significant to the human story of Putney. And it has to do with where Putney Center ended up developing. This is a picture looking in towards the village of Putney from the Connecticut River. If we look on another Google map view, and Putney Village is right around here, the center of the village, you can see in the topography that there's the broad, sort of flat valley of Sackett's Brook above the village center. And then right along here, there's kind of a drop-off, a sudden lip that drops down. And right in that spot, there's a waterfall. And this waterfall was an early source of power for the industries that started to take off, notably the paper industry here in Putney that persists to this day, and was able to be there, and the village center formed around the developing industrial center that was all being powered by this waterfall. And basically, when you get a waterfall, what you're seeing is the water passing over rocks that erode at different rates. So the downstream rocks here are more easily eroded than the ones just right upstream. So they're getting worn away faster, and you start to get a drop-off that just gets bigger and bigger and bigger. So right around the center of town, there seems to be kind of a lip of some type of resistant layer in the bedrock that's creating a waterfall there. So again, we have the geology to thank for really the patterning of the community itself and how the village center developed over time. That brings me to another feature of the landscape that's really important here in Putney that takes us away from the bedrock geology. We've been talking about landforms, the Putney Ridge and this waterfall in the center of town that are really governed by the underlying bedrock. But there are some areas of the landscape here that are really being controlled by something other than the bedrock. This is a picture of part of the Sackett's Brook Valley, that nice broad, flat valley. And you can see it's just flat as a bone out here, and there's no rocks on the surface. There's no bedrock poking out. There's no pesky stones coming up, with the plowing. And really in New England, flat is the exception. Most things here are hilly and stony and rocky and all of that. So something different is happening here when you get someplace that's just bone flat like this without any rocks at the surface. And there's a story in that, and it's a story that brings us to the superficial geology of the community, or the history of these loose layers of sediments that are lying on top of the bedrock. And this aerial view of the town looking at the Great Meadows sort of gives you a glimpse at a few other flat landforms here in town, the Great Meadows and some of these sort of terracey farm fields just to the south. This is a sand pit on Sand Hill Road, oddly enough. The road is well named and is actually running over just a big pile of sand. It's a big deposit of sand. And as you dig into it, you can see that this hill here, rather than being a bedrock controlled landform, is just a big pile of sand. And if you dug into those flat areas along Sackett's Brook and along the riverside, you would also find deep layers of just unconsolidated sediments. And to understand why they're there, you have to go actually to a much more recent chapter in Putney's history. And one thing I love about looking at geology is suddenly something that happened 18,000 years ago seems like, wow, that was just yesterday compared to the 500 million year old bedrock. So 18,000 years ago was the maximum extent of the last major glaciation. And at this time, New England was totally covered in a massive continental ice sheet that went down as far south as Long Island and would have covered all of the landscape in over a mile thick layer of ice. So just a tremendous quantity of ice covering absolutely everything here. This is a picture of a modern day glacier. I think this is in Alaska. Just to give you a sense of how different Putney would have seemed. The major difference being that our highest mountain peaks in Vermont were completely covered at the maximum extent of the glaciation. So it would have just been this endless expanse of white. And it seems like geologists think that the part of the glacier that was covering this area originated from an area around Quebec. And the way that these continental glaciers form is if you get temperatures that are cold enough year-round that snow doesn't melt, it just starts piling up year after year. It doesn't melt back. It just gets deeper and deeper and deeper. And as it gets deeper, the weight of all of that snow starts to really bear down on everything that's beneath it. It turns to ice, and it actually starts to flow out almost like a fluid. So you can imagine this cold place in Quebec, and the snow is piling up, and it starts to actually flow out from that center and flow across the landscape all the way down through New England, ultimately. And as it flows across the landscape, it picks up everything in its path that it can pick up. It breaks off chunks of rock from the bedrock. It picks up soil. It picks up sand and gravel and clay and mud and giant boulders and everything. And it sort of smears them across the landscape as it's flowing out. And it covers really everywhere the glacier was. It leaves in its wake this material called glacial till, which is just a crazy mishmash of all of this different stuff that the glacier picked up and moved around. So it's typified by having a range of particle sizes from the tiniest little bits of clay through giant, house-sized boulders, all just mixed up together. A till, incidentally, comes from a Scottish word meaning stubborn land. and so it's the origin of the stony New England soils that are so famous, and famously made it difficult for any kind of large-scale agriculture to really take hold effectively in New England. And this is the superficial geology map of the town, and this orange kind of buff color that covers most of the town, it represents that glacial till. So you can see that most of Putney is covered in glacial till. But there are these areas along the river and kind of going up these river valleys where there are different colors. There are different superficial types sort of superimposed on this till that covers everything. And these different superficial types, rather than being just a mishmash of everything like the till, they're actually sorted by particle size. So you'll get just sand, like the sand pit we saw on Sand Hill Road, or just clay, or just gravel, instead of everything all together. And to understand where this sorting comes from, we have to look to water, which actually behaves very differently than ice in how it picks up sediments and moves them around and deposits them on the landscape. Geologists think that there's ample evidence that right after the glacier departed this region, it left a big dam of this kind of till-like material down in Connecticut that was acting as a dam to the Connecticut River and backing up the Connecticut in a massive lake that went all the way north past St. Johnsbury. And it would have actually flooded some areas of Putney. This map is a recreation of what the shoreline of this lake, which is known as Glacial Lake Hitchcock, would have looked like in Putney. So you can see an arm of the lake coming up the Sackett's Brook Valley here, and another arm coming up East Putney Brook Valley. And all of these low-lying areas right along the river are under the lake water. And if we sort of toggle back and forth between the lake and the superficial deposits, you can see that all of these different colors are happening where this glacial lake used to be about 12,000 years ago is when it would have covered this area. Just taking advantage of the break, I know that this is just a lot of dense material. Does anybody have any questions up to this point that you want to ask before I head on? Louise?
Quick question, we're talking about Lake Hitchcock.
Yeah.
Why was the Connecticut River there at that point?
Ooh, good question, Louise. The course of the Connecticut River has a few different reasons for being. And actually, I'm more familiar with why it is where it is a little further south from here. If you go down to Massachusetts, it actually turns out that as the continent started to rip apart, as Pangea was ripping apart, the continent actually started to split right along where the Connecticut River is now. And so we could have had the Atlantic Ocean opening up right there where the Connecticut River is. But instead, another rift further to the east is what actually opened up and formed the Atlantic Ocean. But in starting to rip apart right where the Connecticut River is, it caused a big fault that dropped a big chunk of land, a big chunk of rock dropped down, and formed a basin that later became the course of the Connecticut River. The river found that weak point and whittled away at it. That fault doesn't quite make it up this far north, so I'm not actually sure precisely what accounts for its position to the north of that fault line that takes it all the way down to where it enters the ocean. But I think it has something to do with the layers of rock, the different rock types, and more erosible layers being along the track of the river, and potentially having something to do with the shape of the folding. Yeah.
I'm familiar with the bows or the holes in East Putney Brook, from the size of a bowling ball to the size that you can actually get into.
And they're like in the bedrock, sort of.
And the water flows over.
I haven't seen those exact ones, but where those occur, those are often created actually by rocks getting circulated in a current. They'll sort of get in a little bowl and they'll get swished around and they'll just grind out a hole over time. And if you look at the bottom of those holes, there's usually all these kind of cobbles and pebbles at the bottom. And a lot of times those represent a post-glacial time when the amount of water going through there was much more because the glacier was still nearby melting. And so the streams were much, much bigger and more powerful. So a lot of our streams have those, there's a name for them, potholes. Yeah, they have those potholes, and sometimes people will actually call them glacial potholes. And I think that's in reference to the idea that they were carved out when there was so much more water flowing through, and they were really powerful rivers and able to grind out these sometimes, huge holes. Yeah.
I had always thought, or was taught, that the old hills here were old because they were once like the Rockies, but they were worn down.
Yeah.
But I gather from what you said they were pushed up rather than having been worn down.
Well, they were pushed up and then worn down.
I see.
So the Green Mountains started out, as this ocean basin, and it got pushed way up in this collision of continents, and then whittled down over millions of years. So it's both. If that makes sense. Okay, well, we'll have more time for questions at the end, but just wanted to get the first crop. So I was talking about how ice and water differ in their ability to pick up and transport different materials. If this is a chunk of glacier, it's picking up everything in its path and sort of dropping it willy-nilly as it goes along. And eventually, when it melts away, it leaves, and it just drops everything as it melts, and leaves, again, this till, this mishmash of all these different sediments mixed together. But water behaves really differently. Water tends to sort particles by size, depending on its energy. So if you have a fast-moving stream running down a steep hillside, it might be able to carry in its current clay and silt and sand and maybe even gravel. And it's going to leave behind what it can't carry. So it will leave behind cobbles and boulders that are too large for it to move. And if some future date that stream isn't there anymore, you would see evidence of it in the sediments, because you would find an area where it was just cobbles and boulders without sand and gravel and all these other things mixed in. And it would give you a hint that there might have been a fast-moving stream there at some point in the past. In contrast, a big still body of water, like a lake or an ocean, really can't carry much of anything, except the tiniest clay particles and silt particles that just get suspended in the water column and very slowly filter out over time. So usually in a deep water setting, all the bigger stuff has already been dropped. If a stream like this comes into a body of water like this, the first thing it does when it hits the slow water and slows way down is it drops all the big stuff that it's carrying. It just drops all the sand and gravel. And that's how you get a delta forming. And then it's only the fine silt and clay, the mud, that actually makes it into deep water and filters out where the current is very still and there's not a lot of energy in the water. So in this kind of setting, like we had with Glacial Lake Hitchcock, if that lake were to disappear, you would find the legacy of it in these lake bottom deposits that are very fine sediments that have been, again, sorted by size rather than just jumbled all together. And that's what you find in the wake of Glacial Lake Hitchcock. You find, I'm not going to go into what all of these different colors are, but they're all different flavors of sand and gravel and silt and clay arrayed on the landscape. And you tend to find the sand and gravel in a shoreline kind of environment, or a delta, an old delta, or shallow water. And then you tend to find the silt and clay in what was more a deeper water, lake bottom kind of setting. And there are a few little slivers. These are mapped out as clay, these little areas highlighted in red that you can find here in Putney. Most of the clay has got sand and stuff on top of it. But it's kind of cool when you can get a cross-section of this clay. It's called varved clay, and it's stripy. And the stripes represent annual changes in the kinds of sediments that were being deposited. So one set of dark and light bands indicates 1 year of sediment deposition, where in the summertime you get slightly coarser sediments as you have summer storms and streams coming in and depositing larger materials. In the winter, if it freezes over, as it certainly would have in the colder climate just after the glaciers, the water becomes very still and the finest particles settle out at that point. So you get a band of finer particles and a band of coarser particles combined to form a year. It's actually allowed geologists to go back and count those layers and figure out how many years this glacial lake occupied the Connecticut River Valley, which is pretty cool. And the clay actually also supplied an important building material to early settlers of Putney. And you can see the evidence of this in this road name. Obviously there's not a brickyard there anymore, but there was in the past. This is right near one of those clay deposits. And if you drive along the river road, you'll notice a lot of historic, mostly early 19th century houses built of brick, almost certainly built of local bricks made from this glacial lake bottom clay deposits that you find in town. And I just wanted to look at a series of landforms, right, coming down along East Putney Brook on East Putney Brook Road, or Falls Road. Thank you. So we're right in this area and heading downhill towards the river. And again, we get these flat landforms. And as we turn towards the river, you can see this is one terrace, and then there's a level that goes down, and then there's another terrace beyond that. And if you keep going down the road, you keep hitting additional sort of these flat terraces all the way down to the level of the river. And this is the work of the Connecticut River itself. It's a little hard to explain, but if you can imagine this as the Connecticut River Valley, filled with these glacial lake sediments. When the Connecticut River actually started flowing again, it wouldn't have been down at the elevation it is now. It would have been flowing on top of these lake bottom sediments and actually, working its way down through the sediments over time. And as it moved, as it would carve down to the next level in the landscape, it abandons its old floodplain and leaves a terrace up higher, and then it does the same thing again. And you get the sequence of these old floodplain terraces that are now far from the river. But it's fascinating when you realize that, because you realize the Connecticut River was way up there on the hillside. And it changed so tremendously in the past 10 to 12,000 years since the glacial lake drained away. And incidentally, those terraces also provide great farmland, and it's really some of the best farmland in the town, where you have so much of the landscape covered in till, which really is difficult to farm. And then you have these flat terraces with fine sediments that have been sorted, so you don't have the big rocks coming out of the soil every time you plow it, and it's flat. And these have been concentrations of persistent agricultural activity throughout the history of the town as a legacy of Glacial Lake Hitchcock. And again, this is the lowest terrace. This is part of the Great Meadow, which is part of the more recent active floodplain of the Connecticut River. This is a map of the good agricultural soils, the best agricultural soils in town. And although they are scattered throughout town, there's really a concentration of them in those areas that match those sorted superficial deposits that I've just been talking about. So a lot of the best agricultural soils are found in the areas that were under Glacial Lake Hitchcock. And again, the lake sediments themselves provided particularly farmable soils. And these are also the areas where agriculture was able to actually make it all the way through to the late 20th century and even to today. This is where you find the active farms that are still surviving here at Putney. So the last segment of this talk is going to be a lot briefer than everything that we just went through, but I want to switch over to thinking a little bit about the local hydrology through the work that Ann Carey did. And I'm not going to get that deeply into this topic, in part because it's a really difficult topic to talk about. When you start thinking about groundwater, how water is moving through the land, through the rocks, and through the sediments, as you can imagine, it gets very hard to know what's happening because it's underground. And sometimes it's very deep underground, and there's structures in the rock and so forth that there's almost no way for us to figure out what they are from up here on the surface. So there's a lot that's not known in any given place about how the water is moving through the land. But there are some things that we can say about it. And this work that Ann did of collecting the well data was a really clever way to get some windows into this question of how water is moving through the landscape by looking at what's happening in these wells that are drilled into the bedrock. And again, we were really surprised to find when we talked to a bunch of local geohydrologists that this is cutting edge data. This is not just a known pattern that's old hat, but actually something they were really interested in our result. So it's something that geohydrologists have been hypothesizing for a while, that these marble-based local rocks would probably carry more water than the non-marble ones, but they don't actually have a lot of data about that. So Anne actually did work that is right on the cutting edge of what's being done, which is really cool. And the other side to what Anne did started with a question. I think, was it Tom Goddard who asked you this?
Yeah.
He said something like, well, Anne, you're looking at the hydrology. Answer me this question. This is a little zoom in of the area around the Putney Central School, roughly. And this here is the Putney Village well. And up here is the Putney Central School well. And they're really pretty close together on the landscape as a whole. It's not all that much of a distance between them. But the Putney Central School well, the water in that well has a pH that tends to be around 8, which is on the basic side of neutral, neutral being 7. And the Putney Village well tends to have a pH more around 6.6, which is on the acid side of neutral. And it might not seem like a big difference, but since pH is measured on a logarithmic scale, there's actually many hundreds of times more hydrogen ions in the Putney Village well water than there are in the Putney Central School well water. So Tom Goddard, I guess, had been pondering this for quite some time and wondering, how could these two wells that are really pretty close together have such a different pH? It sort of indicates that the source of the water is there's something very different about it. So he said, tell me why, Anne. And Anne said, I don't know, but I'll find out. So one of the main differences between these two wells is that the Central School well is drilled into bedrock, and the Putney Village well is in one of these glacial Lake Hitchcock surficial deposits. It's in sand and gravel, so it doesn't get down into the bedrock. So that's really probably the most significant difference between these two wells and between where the water is coming from in these two wells. So Anne was curious about whether this pattern held up across the landscape of wells that are close together, where one is in surficial materials and one is down into the bedrock. Does that pattern of a difference in pH hold across the landscape? So she went out industriously knocking on people's doors and getting samples of water from their wells and sending them off to have them analyzed. And I'm going to just sort of focus. She got a lot of different data. I'm just going to focus on a few points to sort of bring out the pattern. Up here on Fort Hill Road, the circles are going to indicate these shallow wells in surficial materials. And this is a shallow well that had a pretty low acidic pH of 5.64. And then right next to it, the stars are all these bedrock drilled wells. A pH of 7.7. So again, we're seeing that same pattern. These wells are almost on top of each other, but the water is really different. And here's another bedrock well in that area, pH 8.26. So we're still seeing this pattern. And here's another different location around East Putney Falls Road of 6.1, and the neighboring bedrock drilled well at 7.4. Now, if we scratched our head a lot about what was causing this, and Anne talked to a lot of geohydrologists and read a lot of complicated papers that she really did her work to slog through the technicality of it. But there isn't a clear answer that comes out of this. But here's what we came up with after talking to a lot of people and reading a lot of papers and thinking about it. If you think about water moving through surficial deposits like sand and gravel, this being sort of an illustration of what the air spaces might look like between grains of sand. There's a lot of space between those grains for water to flow through quite quickly. So potentially rainwater could just fall on the surface, percolate down, and be in somebody's surficial well just in a few hours or a few days. it's not a long transit time potentially from the water hitting the ground and getting into your well. Whereas to move through bedrock, there's really no spaces between the mineral grains in the rock, unless you're talking about potentially the marble areas of town. The water's all having to move through little fractures and cracks in the rock that are of different sizes. And it's a much slower process for the water to make its way through the rock, potentially as deep as 800 feet, where some people's bedrock wells are dug all the way down to. So it's probably a much longer transit time from water falling as rain on the surface of the land to actually making it into your bedrock drilled well, hundreds of feet under the ground, through all these tiny little crevices and cracks in the rocks. And one thing that seems to happen as water spends a lot of time hanging out with rocks is that there are chemical interactions between the water and the rock over time, and the acidity tends to get buffered by the minerals in the rock over time. Now, the schists and slates that are so common around town don't have a lot of buffering capacity in them. So one idea that came out of our conversations with some of these hydrologists is that the fact that some of these pHs are so high in rocks that don't really have a great buffering capacity might indicate that the water has been in there a long, long time. And it may have taken even hundreds of years for the water to make it from the surface of the land all the way through those cracks and crevices into your bedrock drilled well. So that may be one of the factors, whereas the shallow wells are reflecting more the pH of rainwater, which tends to be acidic, and even more so these days than it once was. So there isn't a lot of that time to interact with the minerals and get buffered. So that would be a pretty interesting result if that turns out to be the cause, potentially indicating something very significant about the water that most of us use, that it may have taken many, 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 many years to actually make it to your well. It might even be reflecting things about the climate, 100 years ago or more, and not necessarily immediately reflecting things that might be happening today with the amount of rainfall and so forth. If we look across the whole town, this is sort of all of Ann's data for Putney, and some of the places have a stronger relationship than others. The lighter the symbol, the more acidic the water was, and with these darker ones being the most basic. And in a lot of places, it holds true that the bedrock drilled wells tend to be less acidic than their neighboring surface wells. And this is, if we take all of the data that she collected, this is the range of pHs for those surface wells, and this is the range for the bedrock wells. So they overlap quite a bit, but overall higher pHs, again, for the bedrock drilled wells. And there's a couple places that stand out where that just doesn't hold true, where there's virtually no difference between the two. These are the two sort of sections of town where the data she collected really showed no difference between the two things. And if we switch over to looking at the bedrock, I think we find some explanations for that. This area here is all in that patch of bedrock that contains a lot of marble. And so I think what may be happening is that there's so much more calcium carbonate in that area of town that even in the shallow wells where the water hasn't been percolating around a long time, there's enough buffering capacity that the water's getting buffered in those shallow wells, even if it doesn't spend a lot of time working its way through the rocks and interacting with the minerals. There's just a lot more carbonate in the soils and so forth to do that buffering. That's one possible explanation for why you don't see the difference.
Claire, just an interruption. What are the stars versus the circle?
The stars are the bedrock drilled wells, and the circles are the surface wells.
What is a surface well?
Well, they are wells that were not drilled into the bedrock. So they're either they're usually like in sand, like you might call it a dug well. Somebody, a lot of them are historical, you know, when people weren't able to drill a deep well, and they just dug into the sand that they had on their land. And
We had a dug well at 6 feet and a drilled well at 330, so that's kind of what you're talking about.
exactly, yeah, exactly. The other area that has this pattern is not on the calcareous or the calcium carbonate containing bedrock. So it was a little bit of a head scratcher at first, and I thought, oh, I gotta throw out that whole idea, it doesn't work. But it turns out that all the points are along East Putney Brook. These are all wells that are right along the brook. And the brook flows down from this area of marble bedrock. So probably the water in those surface wells is associated with the water of the stream. It's probably the water that's being, you know, moving down through the landscape in East Putney Brook. And it's coming down right off of that marble-bearing rock. So it's probably that water is already carrying that calcium carbonate from the marble rocks. It's already buffered from its travel over those rocks. And again, you know, these are ideas based on knowledge and based on people's experience that might explain these patterns. But this is also, as I said, it really is cutting edge stuff. And there's a lot of things that scientists just don't know about water chemistry and how it interacts with rocks and how long it takes to move through the rocks and so forth. There's a lot of black boxes in there. So I don't want to present this as, you know, the facts, but just suggest the ideas that we were able to come up with in our conversations with some of the people who specialize in this stuff about why Anne was finding these interesting patterns. But I think that it could potentially have some very interesting implications for the future of our water supply, and with folks getting water from bedrock drilled wells. Potentially, if it does take a very long time for water to get into people's wells, we may see a big lag in the response of our wells to changes that might be happening in the water supply at the surface. And it might potentially make people not realize that there could be problems, whether there's a change in climate and there's less rainfall, or a lot of these bedrock wells are getting recharged, or the water is ultimately coming from higher areas, from hilly areas, where the water is seeping into the rocks and flowing down into the lower areas. And if you were to go in a forested setting like this and cut off all the trees, it would completely change the amount of water that made it into cracks in the bedrock. It would just be a whole different place. And people might find, you know, miles away that potentially it could have an impact on somebody's bedrock well that was potentially delayed by some amount of time. So I think it just might suggest a need for some real forethought about a lot of types of changes on the landscape that might have influences that we can't predict very well. But another suggestion we got from one of our geohydrologists was that there might be certain areas in those upland settings that are particularly important for the water making it back down into the bedrock crevices. And who was it who suggested that the upland wetlands?
The USGS, the United States Geological Survey.
Yeah, I can't remember his name either.
It'll come to me.
Well, one of the fellows we were talking to was suggesting that upland wetlands might be particularly important places for these bedrock wells to get recharged. Because they're places where the water can hang out on the landscape in one place for a long time and have time to seep its way down into all of those cracks and so forth that are running through the bedrock. This is an aerial view of Bear Mountain, looking at, you can see the fall colors turning early in a swamp up here. This is actually a rare community type that you have here in Putney. It's really neat black gum swamps, and there's a few of them up on Bear Mountain. And that might be an example of the type of setting that could be important for recharging these bedrock wells. We also went to a conference of geohydrologists where we floated that idea with a couple other guys who were like, nah, So it's hard to know if it really is critical.
It was
But
Greg Welch.
what's that?
Greg Welch.
Greg Welch. And another example of a community that might be important for these bedrock recharge areas would be vernal pools, these areas that fill with water in the spring. And again, that water sort of sitting on the surface may allow a chance for water to make it into that system of cracks. And I've just sort of visualized this with, we cut into the landscape and imagine the bedrock with this network of cracks and these wetlands kind of sitting up here and just giving time for water to slowly, percolate down into that system of cracks and potentially recharge these bedrock wells. And that is all I have for you tonight. Somebody pop the lights back up. And I'm happy to take any questions that you may have. Yeah.
Is the Putney town well more shallow than the Central School well?
Yeah, significantly. I think it's about 50 feet deep, but that's all superficial materials. So that's a deep deposit, sort of glacial-related deposit of sand and gravel. That it doesn't go down into the bedrock. I'm not sure what the depth is on the Central School well, maybe a couple hundred feet or
500.
500, so much deeper.
So is there a chance that, it's not happening now, but in the future, when there's more population, more people have to, in smaller areas, that you'll have too many people drawing the water out and it'll be depleted and then it can't refill fast enough?
I think that's a possibility, yeah. And it's hard to know, especially with the bedrock, what the origin of the water is for any given spot. You've got this network of invisible cracks under the ground. You don't really know what's connected to what's coming from where. You could have two wells really nearby that are totally unrelated in where the water's coming from. Or you could have a bunch of wells all together that are drawing from the same fractures and are really going to influence each other. I think most well drillers, do some testing to see if your drawing water is influencing your neighbors. And certainly they did all kinds of testings when they did the village well to determine, what the capacity of that well was and whether they were influencing other things hydrologically by drawing water out of there. But it's kind of a black box in a lot of ways, and I think it certainly is possible.
Mud spin could also filter down.
It could. I guess the thinking about the bedrock wells is that the water has to pass through so many cracks and crevices that contaminants usually get filtered out in that process. And that's the theory about why to get your water from a bedrock well instead of a surface well where contaminants could much more readily just percolate into the sand and so forth. So the generally accepted idea is that the bedrock, the process of moving through the bedrock tends to filter contaminants out. I don't think that means that it couldn't happen, but
Oil is lighter than water, so
But just to the previous question, the well drillers and plumbers' comments are that the water table is dropping. So we have a well of 330 feet with a static level is at 30 feet. No, it's 30 feet below the ground is where our column of water is. They're saying that's now lower. So they, instead of drilling at 300 feet, for example, they go to 500, which has some of the wells below the river. But it's just, data, small data.
yeah. Yeah, and I'm sure that there's a lot of things that influence that from, climate change is going to be a big question mark in terms of amounts of rainfall that this area will see and how that might change. It could be more, it could be less, and that's all things that will affect eventually or more immediately, people's water supply. Yeah.
What is the mineral deposit that you're apt to find? We have both a drilled well and an old spring, and they both have a considerable mineral deposit. I wondered whether it was calcium or.
Could very well be calcium.
It's
pretty.
I just wondered where the well was, where your well
On
is.
West Hill, above West Hill Road.
There's some marble up there.
There's marble, there's definitely marble at the school. So it's probably calcium carbonate coming out of the marble. And your water's probably a little bit hard. Because if you
Yes,
have
it's
this,
hard.
yeah,
It's hard, no.
yes, it's happening here. This is the calcium carbonate.
John?
This is a story from Dummerston, so you may or may not want to believe it. But our well, which is in an area where there's no marble, at least on the surface, and a very low flow, and it's probably not in a marble aquifer, and yet it has calcium carbonate in it. So there's enough calcium carbonate even in those rocks that are not considered marbles to be there. If you evaporate all the water, you get the Boiler scale. That's what that is.
Yeah.
Even so. Now it may be somewhat discolored, like the water that we had, the deposit you end up with at our house is a little bit discolored. That could be iron from the pipes, or it could be that there's a little bit of iron coming out from the rock as well. So probably calcium carbonate with some sort of impurities in it.
Yeah, Pamela.
Claire, I just wanted to remind anyone who's interested, at the beginning of the program, I mentioned that Ann Carey actually wrote up her study that she did for the Place Project. And it's, actually Arthur has it in his hand right here. It's going to be published and available to take out of the library and at the town hall next week if anybody's interested in more information and in actually looking at the details of her study. It may have more relevance now that you've seen the program. And also this program that you have seen tonight and the other two programs that were previously presented with the Place program will be available to check out of the library on DVD sometime in early December.
So if you weren't able to absorb every detail of Bedrock history, you can watch it again.
Are there implications for dowsers?
I'm sure there are. I don't know much about dowsing, but I don't see why not. I mean, in terms of finding channels, under the surface where water is flowing and so forth. Yeah.
I just want to ask you a question, if I can remember what it is. Thinking that the town well is shallow, it is even more important, I think, to protect the area around it and leading into that well. And I think that's something that we all as townspeople have to really think about. And the other thing is, I think that most of the drawings that you did are yours, aren't they, in the show? So she's an artist as well as a great scientist.
Thanks, Jackie.
Are any of your pieces available, those slides? Or is it enhanced material?
Yes. I don't think those are at the library yet, but I can potentially make just a copy of the PowerPoint itself where you could access each of the individual slides if that's of interest. So I'll talk to Pamela about that. Yeah, I saw a hand.
I was wondering if you'd be willing to consider coming back and doing a field trip so that we could actually go out and look at some of these.
Well, we did do one last time with the original series, and actually you have John Warren here as a local geologist who actually headed up those field walks that we did originally with the program. So, John, take it, John.
Would you really?
Yeah. Not during hunting season.
And for those of you who don't know, it does start Saturday, your arrival.
I think you had a question too.
If I may ask a partially unrelated question. In your study of millions of years and the glacial age and so forth, do you have any feeling about climate change related to,
That's
and if you, can you express it?
Sure, that's an excellent question. I could say a few things about that. One is that certainly when you start to look in the deep past, you see how much the Earth has changed in so many ways, and that the climate has changed really dramatically in the past. That's definitely true. But the data seems really solid now that none of those changes in the past happened as rapidly as they're happening now, and maybe not quite as dramatically. But even aside from that, even if it was totally natural and it wasn't, you know, it's not that it had never happened before, still those times of climate change in the past have been times of enormous waves of extinction of species, whole lines of creatures not making it because of the changed climate, and that could be us in the next wave. And I think the data that our own carbon emissions is really contributing to this process, whether it has some natural cyclical component or whether it's all human created, I'm not sure, but the data suggesting that what we've done is really making an influence on it is very compelling. So I guess my take home would be, it seems pretty clear that it is happening, that climate has changed dramatically in the past, maybe not as rapidly, but that it's always somewhat catastrophic for, if you can be somewhat catastrophic, for the organisms that are, you know, trying to make it through that change, and that our activities are influencing this process, accelerating or exacerbating or completely causing this process. So I guess that's my feeling about it.
Thank you.
Yeah. Yeah.
Just one more question. The Google program you're using, is that Google Earth?
Yeah.
I've never been able to get as much detail as you've got. Do you have any pointers on how to look at it?
I don't know. I just, I don't think I was doing anything particularly special. Sometimes it seems like they changed their aerial photos or something. So there are some regions where the photos aren't as good. So there are places on the map where you just can hardly get anything, and other places where the aerial photography they're using is really good and you can see a lot of detail. So it might also be that the places you've been looking, because I think, I can't remember if it happens in Putney, but in Dummerston, there's a seam between good aerial photos and bad ones, like right in the middle of town.
No, they fixed it.
Oh, did they? But for a while, there were whole chunks where you couldn't see anything. So that may be what you were encountering, too.
Thanks.